And you can also
Go
hide
to
that.
and the more it hides, hide floating panel controls. Bye-bye.
All right.
That's
Hello, everyone. Welcome to this seminar. So today we have Professor Eliot Kapit from Colorado School of Mines visiting us. Eliot is an expert in many areas in quantum information, including quantum error correction, quantum optimization, and quantum simulation. He got his PhD from Cornell and was a postdoc in Oxford, New York, and he's an associate professor in Colorado School of Mines. And so it's a pleasure to have him here today. Probably no one cares, but Eliot is basically our first out-of-state seminar speaker since early 2020. Wow. Yeah. So it's great. So I got it. Yeah. And so after this, the next milestone is to buy the cheese again.
Well, I'm grateful to be the first, and I'll let you decide whether I'm the standard everyone has subsequently fails to live up to, or the crappy opening act band that everybody is. So, thanks everybody. It's a real pleasure to be here. I've had a great time in the department so far, and what I'm going to talk to you about today is my proposal to essentially fix quantum annealing. And so we're going to be by talking about sort of very briefly what quantum annealing is, and in particular, what is wrong with it, and what I think is necessary, what I think would be necessary for a hypothetical improved quantum annealer to achieve broadly applicable quantum advantage in optimization problems, which would have enormous utility in that work. Then I'm going to talk about the specific idea that I and my colleague Vadim Mogniasen at City University of New York came up with called RFQA, which I think will achieve the hard physics parts of this whole. Present a variety of theoretical and numerical results on first oracle problem, which is a way of proving that this is capable of quantum speed up at like a more rigorous level, and then a bunch of numerical results on tunneling in one-dimensional chains and embedding. It turns out to be one of the core bottlenecks in quantum annealing design. So quantum annealing, for those of you who are familiar with it, is a non-universal form of quantum computing that can succeed without error correction. And the goal is very simple. It's to find the lowest energy state, or at least a sufficiently approximate ground state, to an Ising spin model that is just a collection of Z and ZZ interactions. And in the worst case, finding the ground state of problems of this form is NP hard and efficient heuristic. So don't expect to guarantee to find the ground state in polynomial time. Efficient heuristic solution methods to solving these optimization problems can be very powerful. And nearly any problem in computer science, and especially any problem in NP, can be relatively efficiently mapped to this form. So with, at least with polynomial overhead. So being able to solve these types of problems efficiently, it would be quite powerful. What makes quantum annealing quantum? Well, how quantum annealing works is it implements a transverse field Ising model. So in addition to the problem Hamiltonian HP that we're trying to minimize, we also add to it a transverse fields term along X at every spin. And the typical way that quantum annealing is done is you start with A of t is 1 and B of t is 0, and then slowly turn down the transverse field and up the problem Hamiltonian. And if you do this slowly enough and don't have to worry about noise, you will end up in the ground state of the problem Hamiltonian HP by the quantum adiabatic theorem. This is, yeah.
Okay, there's a question. So, this spits out a quantum answer, right? The quantum state that minimizes.
You just measure along Z, so this just spits out a bit.
Got it. Okay.
And so in some cases, the HP can be formulated such that the ground state is, the ground state will satisfy every constraint, and so it's efficiently checkable. In other cases, you just have to hope that you're low enough. So this is done physically in strongly coupled superconducting flux qubits, which are tiny loops of superconducting wire, and there are two quantum computational states are persistent current states circulating clockwise or counterclockwise in magnetic fields, and has been commercialized by a company called Dealer Systems out of Canada. And I should say that these flux qubits are very noisy. like all qubits, but these are noisier than most. And at first glance, you might go, okay, well, noise is just going to erase this. Like you didn't mention error correction. This is a quantum computer. D waves, quantum computers have upwards of 5,000 something qubits. So why does this work at all? And the answer is that the physical energy, these qubits are noisy, but the physical energy scales of the qubits, both the interaction terms and qubit energies themselves, are large compared to the bridge temperature. And what this means is that the physical lab frame ground state of this qubit array will solve the problem. And so your task is simply to make this thing sufficiently cold, right? And because it's a spin glass, however, cooling it is not a trivial exercise. It gets caught in local minima. And QA actually works empirically. You sign up for D-Waves Cloud Access. You can submit problems to it for 5,000 qubits, and it will sometimes spit out the ground state, even in the presence of noise. But there are some caveats here. And one is that analytical predictions of performance are notoriously difficult. Trying to say how fast was process of interpolating between the transverse field and the spin glass by the ground state is hopelessly hard analytically. And there's no guarantee QA outperforms smart classical algorithms, even if it was an error-free device. It is not an error-free device, and noise does cause issues. We'll get to it in a moment. But sort of even if it were error-free, my view is that the devices as configured by D-Wave are not capable of achieving broadly applicable quantum advantage for real-world problems. And indeed, given all of the noise and other issues of the real hardware, they have yet to show consistently for a real-world problem in practical interest that their quantum hardware will outperform the best classical algorithms. And usually it does somewhat worse. And we have given a lot of thought to this and drawing greatly on the work of the previous DARPA RFQA program, in particular to me, who's in this room. We sort of decided there are actually 4 reasons why this does not achieve quantum advantage yet. And there are calling 4 problems. One is the computational weakness in uniform transverse field. That just applying a uniform field along X and a problem along Z and varying the 2 is not enough. It's the simplest way to achieve quantum annealing, but somewhat predictably the simplest possible way of doing something is not necessarily the best. There's the second problem I call the time overhead of embedding, and I'll explain what that means in a few slides. And then the first 2 of these deep core physics problems I'm going to address in this talk. The latter 2 are, one is control and precision and crosstalk, that being an analog device, the actual interactions between the qubits are not exactly what are specified by the programmer, which means you may be solving the wrong problem. And this gets particularly messy at large scales. And then second, as following actually did a paper that Tamim wrote a few years back, is that finite temperature is an issue. That even if the system, in absence of noise, we're able, and in a closed system, we're able to find the ground state perfectly, because it's interacting with a cold but not 0 temperature environment that keeps you kind of away from the ground state. And I'm not going to talk about the second 2 problems much, but solving the first 2 is the focus of this talk. And the goal of this talk in fixing quantum annealing more broadly is I want a quantum computer that will achieve typical case quantum advantage for practical problems without topological error correction. Because as Pablo said, I work on error correction. I know what the overheads involved here are. They're ferocious and horrible. And we are many years away from like a surface code type machine. So I'm a busy man. I want a quantum computer soon. And I don't want to wait many more years. And so I think the most natural route is to upgrade quantum annealing. And the 5 design criteria we followed were first to accelerate multi-qubit phase transitions. I'm going to talk about that in the next couple slides. Second is minimize fine-tuning requirements. If your algorithm depends on all kinds of exponential precision knowledge about the problem, it's not going to work if you don't have errors, because you don't ever have that precise knowledge. Third is no efficient classical simulation method, which is necessary but not sufficient for quantum advantage. I then also want to interact favorably with the cold bath. The system's energy scales, again, are large compared to temperature. If my goal is to get the system cold, I want that bath to help, not hurt. And finally, mitigate this embedding problem that I'll talk about in a second. So to talk about why these problems are hard. And it's that, you have you have many interacting variables and it's very disordered. So it doesn't have any kind of regular structure and what these problems actually look like in practice. And the energy landscape of these problems is rough and it's called glassy, which means it has many local minima. And when you're in one, any kind of local, just flipping a few spins and seeing what happens won't tell you anything about where other minima are, how deep they are, how to find them. So you essentially when I talk about this in Colorado, I just point to the front range and say, okay, it's like imagine you're trying to find the tallest peak in the front range blindfolded. Because you can tell what's in your immediate vicinity if you're blindfolded, that I can kind of feel around and see am I going up or down. But as soon as I reach like the local peak, all other ways go down. But that local peak will not be 14,500 feet or whatever the highest mountain in the front range is. And we don't have the benefit of just being able to see 50 miles away. These are quantum spin glasses, and so fortunately, local minimum escape is possible through a mechanism called collective quantum tunneling, where because of the transverse field, large clusters of spins can flip simultaneously to tunnel through that high energy barrier and reach other states and explore that space more efficiently. This is the core difference in my mind for our quantum annealing from smart classical routines and the likely source of broadly applicable quantum speedups. This sets the difficulties. This has been proven to set the difficulty scaling at large and in quantum annealing. And you can formulate any problem to be bottlenecked by a very specific event of this type. The catch, though, is like all quantum tunneling processes, they're generically slow. And in particular, the rate at which this happens increases exponentially in system size. It's exponentially increasing in the number of spins that happen, but that is increasing with system size. If these processes were sufficiently fast, then you could achieve polynomials, exponential speedups, and optimization in machine learning. Right. So if I have a quantum computer that has a tunneling rate of 1, regardless of problem, I've collapsed the entire polynomial hierarchy. We do not have such a machine, but can we make it faster? So criteria 1 is accelerated such phase transitions. The second issue is fine tuning. If you generically expect exponentially small gaps, which is equivalent to an exponentially small tunneling rate, you can speed up in the adiabatic theorem by sort of slowing down when you know you're right near that resonance point and letting the system tunnel more efficiently. However, to do that, you need to be able to hit that target with exponential precision. And you don't know where that is generically. And it turns out that finding that is, from a classical point of view, is actually harder than solving the problem in the first place. All of these cases where noise-free cases, or with noise, or with a bath, you have the same quadratic tunneling scaling, where you do a tunneling rate because you're off resonance scales as the minimum gap squared over the energy range swept over. And we want something that provides an advantage in that regime. And without fault tolerance, you'll have some level of noise, and so avoiding that is hopeless. But even with fault tolerance, you end up in this problem. But fault tolerance also brings its own severe slowdowns. I highly recommend. There's a paper from Google on PRX Quantum in 2021, where they carefully estimate the time overhead of fault tolerant quantum computation. Conclude the quantum speedup, that a quadratic quantum speedup, where you take the square root of the number of steps, is functionally worthless in practice because the prefactor disadvantage is so severe that you only see the quantum computer win when it takes many years to solve. And so we cannot rely on fine tuning for any of these other scenarios. We also don't want to avoid what is called the quantum Monte Carlo loophole. So efficient classical simulation boosts quantum advantage. And it turns out that in the noisy limit of a uniform Francis field with slow variations, you can actually often simulate this with quantum Monte Carlo, a classical method. QMC is not practical to actually solve these problems because it has a huge prefactor disadvantage, but can outperform G-Wave. And so that efficient simulation means we're not taking full advantage of the system's quantum nature. So we need our upgrade to quantum annealing to be proper quantum, exponentially hard to simulate for all classical methods in the generic case. And likewise, the system has a cool bath. This is not a bad thing necessarily. It acts as an entropy sink. It's the main reason we don't, it's the only reason we don't need error correction. This is error correction. Error correction is that the fridge is 20 millikelvin. That is the error correction mechanism for annealing. This can be a problem-solving resource, as shown by the NASA group, starting in 2018, and a bunch of papers that followed. They showed that in D-Wave, you could actually pause somewhere near where you think transition is and just let it sit there. That'll solve the problem hundreds of times faster than the default method, because it's cold, right? It's a cold place. And I've written a number of papers that show this has that actually simulating this bath faithfully is extremely difficult. That simulating the full quantum dynamics of a finite temperature disordered system is colossally hard and actually much harder than the closest together. And so if it's always here and it can potentially help, we want whatever we do to fix quantum annealing to interact favorably. Right? And then finally, I want to talk about embedding. So D-Wave's quantum annealer is and all feasible quantum hardware is a two-dimensional grid of short-range interacting flux qubits. And logical problems do not have that nice short-range structure. A problem in task optimization, like logistics scheduling, is not going to elegantly map to a two-grid by default. And so what you do is you do a process called embedding, where you take single variables and map them to a long ferromagnetic chain strings across the processor so that you can connect it to distant objects. And there are other ways to do embedding, but that are all have the same problem in terms of. And the space overhead is roughly quadratic. You can show that if I have an arbitrarily connected problem and of n variable, I will need order n squared with a prefactor that depends on the local connectivity. But quadratic overhead is not that bad. Like, that's not horrible. If we could follow a Moore's law with quantum hardware, then quadratic overhead is not so severe. But the problem, so that's the space overhead of embedding. That's what a lot of people point to. But there's a much nastier problem with embedding that are referred to as the time overhead, which is that when we're annealing our quantum state and we're trying to reach them, it turns out that these chains in a disordered problem will freeze at different times. And what I mean by freeze is they freeze into the ferromagnetic configuration. And if that's frozen into the configuration that it should be in the ground state, then that's great. But if it's not, that long object all has to simultaneous tunnel. And for n spins in the ferromagnetic phase to tunnel all at once, that rate decreases exponentially in the length of the chain. So this is an exponential time overhead penalty. And this is common to other embedding schemes as well. And it leads to a really ugly trade-off if you've ever tried to program such problems into a D-Wave machine, because you essentially choose the strength of the couplings within the chain. And if you make them too weak, then it's more fragile than noise and you can have logical uncertainty in your ground state. If you make it too strong, the chains freeze early and that exponential slowdown sets in much faster and time to solution explodes. And so you have essentially exponential penalties in either direction. And unlike the space overhead, we can't just make the system bigger. Right? I can make a colossal processor with 10 times many qubits in every direction, but if this is still limiting me, that doesn't help. And so if this is an unavoidable problem, we want to at least reduce the slowdowns from the schemes. So these 5 core criteria are accelerate phase transitions, no fine tuning, no simulation possibility, tolerates cold bath, speeds up embedding. And I believe that an upgrade to QA, at least where 1 and 5 are strong enough, is very likely to achieve broadly applicable quantum range. And so what is this? Well, I'm giving this talk to propose such an upgrade, and we call it RFQA. And this is a paper I wrote with Eliot and it's in Quantum Science and Technology in 2021. So RFQA is a double meaning acronym for random field or radio frequency quantum annealing. And the core idea is very simple. I leave the problem alone, it's the same, and I modify the driver Hamiltonian, which is the transverse field term, to apply an independent oscillating term to every single qubit. And there's a lot of ways to do this. You can oscillate all kinds of different things, but I just try to oscillate something independently at every qubit. Right? And the 2 simplest and most studied versions are RFQA-B the direction of the transverse field, instead of just pointing along X, wobbles back and forth between X and Y. Or the magnitude of the transverse field, where it's multiplied by 1 plus alpha sine ft, where alpha is less than 1, is swinging up and down. Right? And it turns out that if you arrange this and choose this cleverly, I think this is sufficient to solve all these problems. And so to help understand, let's see, this is kind of technical, but basically we go through this in a lot more detail in the paper, but to basically help understand it, we proposed this conjecture called M scale. It turned out to be it's a conjecture, but it's extremely hard to violate, and we believe it to be true in most cases. Basically what it says is that for near a phase transition, where we have some exponentially small gap, then all local operators to mix those two competing states are also going to have exponentially small matrix elements. And what the M scale conjecture says is since it's a disordered problem, some operators will be stronger than others in terms of trying to mix the two states. But what the M scale conjecture says colloquially is that those operators will be exponentially small as well, and that exponent is the same as the minimum gap. And it turns out, again, this is very hard to violate, and if you assume this is not true, you will get weird unphysical things. And it's provably true for everything I worried about in this talk. But if you assume this doesn't have to be true for RFQA to work, but if you assume this, it makes all the subsequent analysis much easier. So again, if I'm trying to mix the two states through some product of spin operators, that's all going to be exponentially decaying, and it's decaying with the same exponent that this tunnel is. It's just precise. So the basic mechanism of RFQA is Eliot, please.
So the immediate criticism one can make, but now you need individual control of each qubit. Right?
Yes.
So now you have introduced all sorts of new control lines to your device. And the original motivation for QA, or one of them, is that it was simpler, right? You didn't need so many control lines. So what's your sort of argument against that?
Okay, no, so that's entirely fair. You do need these lines. You don't need to use, you can pipe the same frequency to multiple qubits, so there is some level of multiplexing you can get away with. And it actually, as a result of synchronization, it shows you want to do that, and you get better results than what I present here, but that's in progress work. And so I'm not talking about it because I'm completely positive of all the things there. But it is simpler, but it turns out simpler wasn't good enough.
Sure.
And so this is more complicated, but vastly less complicated than surface code. So this is this is more complicated, but the next step of complexity rather than a colossal leap. Great.
Can I ask a question about this conjecture? So I understand. I mean, it seems intuitive in the sense that these G1 and G0 are certain spin configurations. They're not that
Very far apart.
and they're not the eigenstates of the system. And your O's here are some
Operators.
and they're the things that would generate the couplings that lead to the
Well,
gaps
so
in
the
the
idea is that
place.
if you're near so the gap is exponentially small. But based on whatever parameter tuning, you might be like order of 1 energy apart. And you can't, because that gap is exponentially small, you're not mixing them at all. This is the normally. But now imagine I'm applying a bunch of oscillating perturbations.
Okay.
That's what these operators are going to look like.
Okay,
And that's why I'm worrying about this matrix element.
that's here. Okay.
Okay, so let's say we just have one spin oscillating and we're near this phase transition. So this is just some cartoon of two competing states and then avoided crossing, right?
Okay.
Well, we have the main avoided crossing down here. That's not changed by one spin oscillating in some way by any meaningful sense, because this is some many spin tunneling event that sets this. But now, if this is some frequency f, when the energy difference between these states is f, then there is a non-zero matrix element to do this. And M scale says it should be proportional to this. It's generically going to be smaller, but have the same scaling as this. And so long as the spin we're oscillating participates in the transition, you generically, this kind of Gelman's totalitarian principle says that everything which is not forbidden is mandatory. Any process that is not forbidden by symmetry in physics exists at high enough order of perturbation theory, and this is exploiting that and really running it into the ground. And so, but this has the same thing, so this isn't any faster. We now have 2 more chances to mix the 2 states, all that weaker ones, and you think, okay, well, that's fine, this doesn't really do anything. Let's say we have n spins, which need not be all of them, but n spins that participate in this transition, all of them being oscillated at n. And I've just drawn 3 here for simplicity. Well, you naively think, okay, well, if these are n different frequencies, every time it crosses one, there's a chance for states to mix. And the rate at which they mix at those transitions has the same proportionality as this one. So this should provide a factor of n improvement, right? And when I first was trying to formulate this idea, that's what I guessed. But that's actually a colossal underestimate, because there's every second order process, right? At every time I have a combination of 2 frequencies, that's a second order process where it absorbs 2 photons from the driver, absorbs 1 and sends 1 back out. And that is going to be even smaller, but smaller by a number that is turning out to decrease exponentially in the order of this, but multiplying something that has the same scaling as this. And there are n squared, there's actually 4 n choose 2 to be precise of these resonances. And at third order, there are 8 n choose 3. So the number of these high order resonances that the system is going to cross explodes exponentially. And of course, the nth order matrix element is going to be really weak, right? These, 50 photon process is not going to be fast, but there are there are 100 choose 50 of those or something like that. And if we assume that the leading dependence of the average m photon resonance is exponential decay with m, so omega naught is the tunneling rate at the phase transition, and lambda is a number less than 1, it's going to decrease exponentially in m, but have the same overall scaling with system size multiplying. And if this is the case, you can actually just sum all these contributions in Fermi's golden rule, because they're all very weak resonances. They all just have a tiny chance to kick the system. And the total off-resonant tunneling rate is multiplied by a factor that is exponential. In this case, I guess I switched notation by accident, so k is the number of spin flip here. You're multiplying the tunneling rate by a number exponential k. And this is the mechanism of RFQA. And I'll go through a bunch of examples of this. All of this I want to pause. This is a new quantum speedup mechanism. This is not in any other algorithm. And this is a new way to defend, because again, if you can make tunneling sufficiently fast to escape local minima, that is a source of algorithmic quantum speedup. And this is a new route to it you don't see anywhere else. And it comes from this exponential proliferation of weak resonances that comes from having a lot of different frequencies applied at once. Yeah.
Is there someone how important is this that k is large?
So k is the number of spins that participate in the transition. And so the problem is only hard if k is large, right? Because if it's a few spin transition, that will happen quickly.
So I guess what I'm asking is, could you check this for a moderate size k to just do the simulation? And
yeah. Oh no, I'm going to present it.
Okay.
Yeah,
sorry, I haven't read.
You don't always see it. So when k is really small, you don't always see an advantage, because there's often there's a pre-factor disadvantage that sometimes shows up depending on which formulation of RFQA you're using. So it at 5 to 10 spins, it might not be faster, then you start seeing it scaling the burdens. Yeah.
So I'm thinking about this and remembering, that sometimes finite temperature helps quantum annealing. So my question is, how important is it to know these frequencies? Or is this okay?
Get to that. So they're drawn randomly from their range, and the argument I could say extends to if you're trying to thermalize in some band of well-separated states, because it's just Fermi's golden rule. So I'll get to this frequency concern now, because there's an important concern that is heating.
Yeah.
Right? Is that I'm applying a whole lot of oscillating stuff to the system. Why doesn't it just boil into temperature? Right? Because that is the default expectation. And off-resonant excitations from these drives can proliferate local excitations, and it won't return to a ground state without a bath. If you have a bath, that might balance it out, and that's okay. But even the closest system, this actually still works, because at first order transitions, these states are usually locally gapped. So your minimum gap, if you have 2 competing states, is exponentially small. but the cost to flip a single spin starting from either of them stays like order 1. And so as a result, we can choose the frequencies to be large compared to that exponentially small minimum gap, but small compared to the order 1 cost to flip any one of the spins. And so if I choose Fj to decrease polynomially in system size, then the heating rate turns out it's essentially the local, it's called a local adiabaticity condition, where it's adiabatic compared to like heating the system by flipping stuff, but still diabatic compared to this tunneling rate that we want to accelerate. And I can even exponentially suppress heating. And so usually we can get the frequencies to go like 1 over n or 1 over root n. And if you put the prefactor too large and then do numerical simulations, you will see the system heat up and proliferate. But if you pick that prefactor even smaller, then it's all fine and it doesn't heat up. And note in a quantum annealer, 1 here is multiple gigahertz. So these frequencies aren't that small. Though if D-Wave went out and implemented this tomorrow, you would probably do 10 to 100 megahertz for each one of these. And likewise, because this is a noisy system, once you have decreased this exponential heating rate to below all the other heating rates that are already there, you don't need to decrease it any further. So eventually you'll saturate that because you'll hit some other scale. Yeah.
Basic question. So here it seems like you're actively trying to let the system go from the ground state to an excited state, but
I'm letting it thermalize quickly in this low energy doublet, but not proliferate local excitations into the high tower above that.
okay, and that happens all the region.
So like say like our 2 competing states that are separated by n spin transition, like this is some omega naught. Great. And then I have a whole ton of other local flip states. And this
I see.
is order 1. And I'm trying to just mix these 2 fast.
I see. So that in the end, when they again separate, like
Yeah.
not
Yeah.
when they're not
And
exponentially
this will
close
not
anymore.
find the ground state probability 1. It will find, like, say, if there's 1 phase transition, it finds a 50-50 mixture out of C.
Oh, okay, so
But if I can get to that 50-50 mixture really fast, then
that's better than always going up.
Yeah, that's
Okay.
yeah, exactly. So the goal is not to reach the ground state with even pretty high probability, just not too small probability.
I see. I see.
And so the RFQA mechanism is really generic, and so the claim is that if you avoid heating, if your M photon matrix elements decay simple exponential M, and if your instantaneous DC tumbling rate is not reduced by the AC terms. And this third condition is more subtle, but can definitely find problems with this here. Then you'll get speed up at sufficient large N. And the source of quantum advantage is fast cold thermalization. So it allows the system to thermalize at a very cold temperature.
What? Right, nuclear turkey.
Well, so I should say, I was trying to think of like what in people's ordinary, I'm a vegetarian, so I don't even eat turkey. But I was trying to think of an example of like what is a situation where thermalization being slow is an ordinary life and it's cooking a turkey, right? Because it takes like 4 hours. So nuclear weapon can cook the turkey extremely fast. And Mike, this is equivalent to thermalizing it quickly without destroying it. Yeah. So, but that's right.
It's good side. Couldn't put it together or try it.
Okay. And this is Sisyphus pushing the boulder. So in our original paper, Quantum Science and Technology, we considered orbital problems, Grover and the quantum random energy model. We chose these because they are structured. They have a classical speed limit of, if I have 1 ground state in the Grover problem or the quantum random energy model, I cannot find that faster than random guessing classically. I need 2 n steps on average to find the ground state, right? And no quantum method, it turns out, there are information theoretic bounds on the speed up can exceed 2 to the n over 2 time. And this is nice because if you're doing simulations and you see scaling that's better than that, you know you did something wrong, or you know you're seeing some transient effect and not like the actual asymptotic behavior. And it turns out that the analytical structure of these problems, because they're unstructured, you can actually calculate what this matrix element rate is, and it turns out to be about 3. And this leads to a time to solution that is very close to 2 to the 3n/4 in this off-resonant regime. And this is obviously not the full Grover speedup, but it's achievable only order 1 precision and has been confirmed by numerics. So we found so you can see this in numerical. These are time to solution from numerical estimates. I'm not going to go through all the parameters. I don't remember what they are off the top of my head, but it is extensive numerics in the paper that show over and over you get a time to solution that's like within error bars of 2 to the 3n/4. And 3n/4 is not an exact number. It's like 0.753 or something like that. It's not, so that's not a special number, but it's really close to that. And in the paper, we also simulated some aspects of the flux qubit noise model. Found that it was fairly resilient to it. Found the same speed up in multiple target states. But the most interesting finding in that paper was that this actually accelerates bath-assisted phase transitions as well. Because what is a bath in a many-body quantum system? Well, it's a whole large collection of independent degrees of freedom at some energies, with some energies that are very weakly coupled with the primary system, right? And I'm just going to think about a single bath spin, because simulating the whole bath faithfully is hopelessly hard. Let's just say I have a single bath spin, and this is the Grover problem with 1 bath spin n equals 12. Right here, here's the phase transition, right? This is what we're trying to hit as a function of the relative strength of the problem, I guess. And then you can see if we miss that phase transition, here's a bath degree of freedom at some energy, and omega d, and we see that when the energy difference between these two states crosses, I now have a new chance to achieve that phase transition again by dumping energy into the bath spin, right? And Gell-Mann's principle, it's not forbidden, so it must happen. And you can see there's an avoided crossing there. And M scale says the minimum gap at that bath scale bath-assisted transition has the exact same scaling with n as the primary transition. It's small, it's smaller by coupling squared. So it's smaller by the coupling, so it's a lot smaller. But and you can check numerically that the ratio, as you extend the ratio of these two gaps to constant. So M scale says this has the exact same scaling as the primary transition, so it's not a speed up in and of itself. And so if we then follow the RFQA argument, we blast it with a whole bunch of low frequency tones, and there's an exponential proliferation of combinations around this area. And you sum up all these multi-photon resonances. But the point is that the bath assisted transition is the exact same thing. It just occurs at a slightly different energy and has 1 more spin involved. But 1 more spin in an n spin tunneling event just means it's that much slower. But it's the same process, it's the same phenomenology, and therefore the RFQA argument says that this has to go faster, and this has to be accelerated by the same relative amount as. And so we checked this numerically. We took the quantum random energy model, put 2 ground states, and put them kind of close by, but not at resonance. Evolve for a time 3n/4. We'll put them kind of close by and close to where the energy difference is close to the bath energy, but again, no exact resonances here. And evolved for a time 3n/4 and found a constant success probability asymptotically. So this is the same speed up. Bath assisted phase transitions are also multiplied by this factor exponential in the number of spins. Which is a cool prediction and a cool thing to see, right? Like it's exponentially accelerating the positive the helpful interaction in cold environment. I also have this paper with my former student, Ji Chung, who's now a postdoc, where we looked at a slightly more realistic problem called the asymmetric magnetization problem. That's an engineered n-spin tunneling event through ground state, and found it. We didn't have an analytical prediction for the speed up in this model, but we found a consistent polynomial speed up. Work is ongoing to further capture more realistic bottlenecks of NP hard problems and benchmark RFQA on them. But again, we saw a consistent polynomial speed up. In this case, slightly better than the quadratic speed up you get with a perfect resonance. We've explored all kinds of other things, other variations of RFQA I don't have time to talk about. And you can find stuff pretty consistently and pretty easy, not always. But question, and everything has been pretty consistent so far. A particularly promising direction, which I'm going to get into in the last section of this talk, is disordered chain handling and embedding. In full disclosure, I always have to, with caveats, this is almost always more effective in reverse annealing or annealing with a pause where you kind of wait and let the states mix rather than just uniformly sweep, because there's a peculiar high symmetry cancellation that would not be realistic to a noisy trajectory, but shows up in numerics. And it seems to be more effective in high disorder cases. And occasionally, with a problem with very high symmetry, you can get these phases to cancel out and some of these things. So this does not always work in every single numerical thing I have tested, but works very broadly. And I would say that the core argument is quite strong. And so, but of course, there are plenty of details and ultimate performance limits in particular that I don't understand. I could not tell you today, even if I knew, I do not know, and I thus cannot tell you what the ultimate performance limit for this in realistic problems is. I think it is very likely to produce big significant speed up. I cannot tell you how significant, because simulating those is just too hard. This is a AC dynamics simulation. You have to see one whole problem. But what I can do though is talk about how I think it's almost certainly going to solve some of the embedding issues. Yes.
Thanks, Professor. So, yeah, I understand correctly that the frequencies are chosen such that they are, so they are chosen randomly.
Yeah.
And they are roughly 1 over n.
Yeah.
So I can understand what that is for the system size that you're doing here, but you have our system, you have 1,000, I don't know, 10,000.
So
What does that
I use
mean?
1 over. So formally, you can actually, it's fine if you want to log it in. Okay, with the right group factor is actually sufficient.
Okay.
But what I do almost always in practice is 1 over root n. And at G-Wave's problem scale, even because the 1 corresponds to multiple gigahertz there, even at 1 million spins at 1 over root n scaling, you get like a couple megahertz. So they're not slow. They're not that small. They would not be that small in realistic hardware. And obviously, your evolution time should be longer than 1 over that. So you have to sample frequencies.
So when you say the Grover partial Grover speed up is verified numerically, you actually go through the whole dynamics.
Yeah.
Okay.
Yeah, just evolve the system under this historical problem. And so there's a ton of these simulations are really expensive because there's a ton of average. It's real time, so you're doing it with a very small time steps. It's simulating a high def quantum circuit, and there's a ton of averaging involved. So we've
And it's also an exponentially large.
Yeah. So that too, there's the 2 to the end, but there's also that like I'm averaging over 1,000 frequency combinations for every data point. Because the prediction is an average over frequencies, but any individual trajectory can fluctuate wildly.
I see.
So you need to do a lot of averaging. We've moved to for any of you who do a lot of simulation of quantum algorithms, the package we now use is Quest. Using C++. It runs natively on NVIDIA GPUs. And the limit in quantum simulation is memory bandwidth, but the memory bandwidth can be like a terabyte a second. So it's like at least an order of magnitude. So I highly recommend checking that package out. All the later data in this. Okay, so embedded. So the goal here is to mitigate if the chains are frozen, we want them to tunnel fast while staying in the frozen phase. That's the goal of mitigating embedding. Why do we think RFQA should help? Well, the tunneling slowdown is growing with the number of spins, but the number of frequency combinations is growing exponentially in the number of spins. So the tunneling enhancement should grow exponentially in the number of spins as well. And there's also, once we know that if a chain has to flip, it all has to flip at once. That's extra information you now have about the problem structure. We can exploit that to try to synchronize things and do, the random choices is assuming no particular knowledge of the problem other than some rough energy scales. Whereas this is knowing that all these things have to flip at once if they do. And that's information that we can use. So the only simulation method is direct integration with Schrödinger equation. We haven't heard. Other members of the team are working on TEBD simulations. We've gone out to like n equals 40 and shown that speed up persists so far in like using matrix product methods, but that's a progress and some not presented that data today. Just say that we have gone further than this, I just don't have any slides. 'Cause it's not we can't simulate an embedded problem because the number of spins would be crazy large. But if we just take a one-dimensional chain and disorder it, that's a pretty good proxy for the core physics problem here. That I need chains to flip fast in a disordered limit. This paper is in preparation. Gianni Mossi at NASA has been the lead on this part. He's leading the paper and gave a talk about this last year training. So we've considered paramagnetic chains of between 8 and 25 spins. You initialize it in all zeros with the chain Hamiltonian and some weak disorder along Z to kill any spurious resonances turned on. Ramp up the transit field kappa to some value less than J, so less than the phase that's still in the paramagnetic phase. Evolve for order and time, ramp down and measure the probability of finding all points. Right, and repeat many times with our RFQA average over disorder, periodic boundary conditions, so with edge effects, and predictably, when we do this, if you have a just uniform field, the tunneling rate will go as average of minimum gap squared. So the time dissolution is, so you see the exponential slowdown. Because again, this is a simple problem, you can compute the minimum gap correctly for up to 40 spins. And so here, blue points are uniform field. Gold is this RFQA method where you apply either tip oscillate the transverse fields or equivalently apply oscillating Z biases. Turns out that's the gauge equivalent to doing that. And in the weaker transverse field cases, you can see that like at short things, there's not really any advantage, and RFQA can even be a bit slower because adding all of this oscillation increases the energy uncertainty between states. But you see a crossover at between 10 and 14, depending on the problem size, where suddenly, oh no, this is a clear shift in the scaling exponent. And in these small cases, the tunneling rate is still clearly exponential, just with a much better exponent. And that's faster, so that's a win. But the phase transitions at kappa equals 1, and that exponent keeps shifting. And when you get out to like 0.85, 0.787, 0.85 to 0.9, in these simulations, again, the phase transition is 1, so we're still not close to the phase transition. You can't tell exponential and polynomial scaling apart from the finite size data we have. That was the motivation part to do these like DMRG simulations that are still ongoing, to try to get further out of the satellite question. And so, for example, if you do either an exponential or polynomial fit, when the exponent gets so small, you can't either fit becomes good. And it is less clear that for RFQA, the scaling is exponential in system size. So I don't know. I'm not claiming I have proven. I'm claiming it's way certainly faster than the uniform field. I'm not claiming I have proven it does not have some very small exponent large size, but this would mitigate a lot of the slowdowns in embedding because the chain size is square root of the system size. The typical chain length from D-wave and embedded problems is often 150. So this is actually similar up to that range. And so this suggests that this could radically outperform uniform fields of annealers and potentially eliminate much of the embedded complexity. You can do even better. It's also a work in progress by pairing tones again. This all has to flip at once, synchronize a bunch of stuff. And we've looked at a bunch of different pairing patterns. This is just one. You can see they're better exponent for paired tones than if you just choose them vertically. And going beyond pairs of 2 as distinct profiles, pairs of 3 didn't see much difference between the 2. So that's why I present that here. But so this is showing that if you do know things about the problem, you can exploit them in this mechanism. So just to circle back, I laid out 5 reports right here that I thought were reasonable. So one is accelerate phase transitions. Yes, it's beyond classical because you see a speed up in the global problem. It's not the optimum possible speed up of a perfect resonance condition, but it's one that shows up in realistic conditions. Doesn't rely on fine-tuning. Every simulation I've presented assumed an energy uncertainty that was order 1 compared to an exponentially small amount. No efficient simulations, AC dynamics. Tolerance and welcomes to pull back. Yes, bath-assisted phase transitions are helpful to problem further. This helps out. Mitigates embedding slowdowns. Very likely, yes, by inferring from disordered change health. That's the only simulation you can do. You can't simulate embedding. But so the simulation I can do suggests, yeah, this should help. And so RFQA appears to satisfy all 5. And so just to conclude, this is a way of improving quantum annealing through independent oscillating terms at every qubit, with the core mechanism and exponential proliferation of loop resonances is novel and not seen in other algorithms. The update, as Tamim pointed, is entirely on the control side. As Tamim pointed out, that is not trivial, that is quite hard, but it doesn't require a whole new qubit architecture or error correction. And we hope to have data from proof of concept experiments done at MIT Lincoln Lab soon. They've had a little issues that's behind schedule, but hopefully this will be tested soon. And in the meantime, all the evidence theoretically and numerically and analytically that we can gather suggests it's a significant, broadly applicable upgrade to quantum annealing. And with that, it's my last slide, so I'll thank you for your time. Happy to take some questions.
And good. All right, questions?
Alright, that's the silly one, but why the Roman ruins or Greek ruins?
Delphi.
Delphi.
Numerical ones.
Got it.
I went there, it's true, I just got answered. But it's answered that.
No questions? Okay. Okay, that works.
Yeah, absolutely.
Go ahead.
Oh, thanks. I wanted to ask about the rover speed up. So were you saying that you can actually analytically show that?
Yeah, so in the paper, we calculate what the decay rate of these higher order matrix elements is, and then when we sum them, that's where the 2 to the 3 and
I
the
see.
4.
I see. So you're kind of like assuming a random distribution and then showing that.
Yeah.
Okay, I see.
Assume the average.
I see.
Yeah, I mean, like, my gold standard for, as a theorist for things, is I need to have an analytical argument that matches the theory, and I don't have yet for all of these. There's lots of different versions of RFQA that one can find, and some are more amenable to this kind of analytical arguments than others, so that's still a work in progress. That's the only one where I haven't yet.
I see. Is it possible to so does it also give you like if the average value is like a typical value, like the variance is not so large that like actually succeeds with high probability, but like
Yeah, the
very rare.
variance, I mean, since the variance is 1 over root number of trials, or something like that, so.
Oh, okay, so
Since it's something exponential, so it's definitely exponentially depending there, you don't have that many rare events for your probabilities.
all right.
It's 10, can be better than 1, it's not gonna be 1, but yeah, so if we do like, yeah, that's something that we're trying to understand better is what statistics look like with the distribution, that's not something I really understand. With Grover, it didn't seem like there was anything interesting. With the 1D chains, that distribution is weirder because it's also not necessarily exponential.
I see.
That's what we're trying to figure out right now.
I see. One.
Oh, no,
Sorry, and I was a little confused with the random energy model, because that also doesn't have any structure basically, right? It's
Yeah.
all random energy, so like why, and I think you were saying that. It
It's
gets constant-
phenomenologically identical to Grover.
Right, but then it sounded like you get constant success rate.
Constant success evolving for time that goes like 2 to 3.
Oh, okay, I see. Got it, okay, thank you.
So it gives it enough time to get.
So which is the same scaling as the.
As the time, yeah, same
Rover, okay, got it. Thank you.
So on the embedding problem, so is this intuition right? Because it sounds like the argument you presented is a little bit like that. A problem that Ben Reichert posed many years ago as a simple example of how you can sort of make quantum annealing fail, which is it's a chain, but you basically have different couplings. Like so, you have a set of couplings J1, J2, then again J1, J2. And the way this makes quantum annealing fail is that basically the different sub-chains go through the phase transition at different times. And so for all of them to get the same solution exponentially.
You need a big tunneling event toward the end. Yeah, this is that same.
Okay, so you're making
It's
you're
a
making
simpler,
it simple, yeah.
it's a simpler setup.
Yeah,
It's a uniform game, just tuned to not hit the transition to environment. But it's the same idea.
So you basically said you kind of force or kind of help them go through it together.
Yeah.
Yeah, okay, good.
I have a couple of questions. I wonder, I just wanted to understand a little better the little drawing you have there. So it seems that if I understand correctly, the whole idea here is that, you're driving this mixing between the ground state and say this first excited state, that there's this big gap. To that prevents the system from heating. And therefore you can get reasonably good probability to get or end up in the ground states.
Yeah.
50%. But do we know that the spectrum looks like that? That there is this, that there's especially small and then there's
This is
this
the
big gap?
generic, so we don't know that for sure. This is the generic phenomenology of like first order phase transitions, it's like that. For a
Okay.
second order phase transition, this gap is like 1 over N or something else. But then this gap is not exponentially small.
Okay.
There are exceptions to that. This is heuristic.
But there's enough evidence that there are problems of interest that have that
Yeah.
kind of spectrum.
And you can definitely formulate problems. for this.
Okay, cool. Yeah. The other question I have is, you mentioned sometime in your talk about the issue about miscalibrations and type of things. So I wonder, does this, I mean, the kind of J chaos that people talk about, the issue that we're not setting exactly these parameters.
So this does not help that.
Is that a problem that you're worried about?
I mean, it is, it was number 3 on the list of
Okay.
problems with quantum mechanics,
Yeah.
I guess definitely is a problem with that. And this does not fix that, they can't. I will say that, my feeling about the kind of J chaos stuff is nuanced in the sense that, all of these NP hard problems are approximation hard also. And so if you could perfectly find the ground state of the problem the system sees 100% of the time, again, that's not given on the spin class. But if you could, then J chaos in most cases would let you to still get a state with similar energy
Okay.
most of the time. And that is still actually NP hard. So it is a big problem in practice. And also, like, the question of approximation hardness in 2D is different from the general statement. These problems are hard to approximate on arbitrary graphs. So yeah, it is a real concern. That's why it's tough to mention in the current talk. It's just fundamentally not something that you can't solve a problem if you can specify well, right?
Another question?
Well,
So one question is like, so, yeah, I guess it's kind of related, but what actually makes it fail when you apply to like NP hard problems?
Well, I mean, so I always want to be careful making statements about that. But like, we know kind of what the typical case cost on it is like these problems. These problems.
Because it's
The problem with NP simulating, well, it wouldn't fail in the sense that it'll probably still do better than uniform field scaling, but it might not be.
right
It's still probably take exponential time. Typical case.
for the worst case, right?
Yeah, for the worst case, typical case versus worst case.
Yeah, it's a different thing.
Not making any claims about that in either direction. But the catch though is that when you try to simulate NP hard problems, is that they're not really hard at like N26. And a lot of the like energy landscape exponentially small funnel disorder mechanisms that are what really makes these problems hard at large system size are not visible at small scales. And so like I've always tried to be very careful and make sure what I'm doing is showing the right exponential scaling that I think it's supposed to be. And that's hard to do. So that's something that's still.
I see.
Yeah, it's hard to attack NP problems directly in something like this. Because the problems themselves are not really.
I see, thanks.
so I'm gonna ask the sort of a, you're optimistic about this for sorts of reasons. And I'm with you, except I'm still thinking about what Ivan said too. There's this issue of control. can you know, this isn't gonna fix it, but why are you so optimistic given the control issues, I guess?
Well, again, this is just like, we're talking, so we know, like, you can easily write down 1,000 spin problems that it would take the Summit supercomputer a year to solve. Right, so and 1,000 logical variables is not that, these are not, 1,000 logical variables is not that much, right? That's like, you know, it turns out that's like about 100,000 dealers. So like, that's not, it's only a few generations later in the current. Right? So, and control error is, you know, it's an issue, but like, when I say I'm optimistic about this, I don't think necessarily analog methods and scale are kind of, but like, it could get to a point where classical silicon is ever catch up before it hits the wall. And then maybe do multiple words. There's a lot of other examples you can put this, but and control error, like, you know, this is just a number, and like also like say control error creates like a, you know, root and energy uncertainty, and this gives you an exponential root and penalty of finding ground state. That gets still way better than the difficulty scaling of the actual problem. It's exponential n. So like there is plenty of room for quantum advantage. Like you don't have to outrun the bear. You have to outrun the slowest camel.
Yeah.
Right? And classical computers are a moving target that is very, very fast runner, but not infinitely fast. So it's okay if this is not working perfectly, so long as it is.
All right. With that, let's thank Eliot for